11.7 notes is over geometric probability. And geometric probability is done the same way you do any other type of probability problem, except we're focusing on length or area, some type of measurement. So let's go ahead and define the two just so you can kind of see what the similarities and differences are between them. Probability is the probability of an event is a measure of an event is a measure of the likelihood that the event will occur. Okay, a geometric is a ratio. It's a geometric measure such as length or area. Okay, so they're both ratios, and we're both comparing two different numbers and seeing what the outcome is. I can leave it as a fraction, as a decimal, or change it to a percent. All right, now, my little person over here that I created, I'm very proud of them. It says to apply the geometric probability formulas, you will need to know that every point on the segment or in the region is equally likely to be chosen. All right, so just make sure it's just kind of like throwing a dart at a board. Every part of that dart board is just as likely to get hit by the dart as any other part. All right, so that's what we're looking at here. First, we're going to do different lengths. We're going to do a probability to see compare two different lengths. It says find the probability that a point chosen at random on Fj is on segment Gk. So we're looking at this entire segment from point F to point J. But we want to know what the likelihood is that we're going to pick a point in segment GK. So GK takes up a major portion of FJ. So there's a pretty good chance that you'll pick a point within this area right here. All right, so to figure out the length of that, a lot of people are just going to count it. Okay, that's usually the easiest way. How far is it from G to K, and how far is it from F to J? Now, the good mathematical way to do this is to find GK as the absolute value difference between the 2 point locations. G is at point -3 and K is at point 6. And -3 minus 6 is -9, but its absolute value is 9. So GK has a length of 9. FJ, on the other hand, is a little longer. Its length is the difference between points F, which is at -5, and point J, which is at 7. The absolute value of those two numbers is 12. All right, so now the probability that a point is on segment GK is the ratio of the length of GK over the length of FJ. All right, so that is 9 to 12, because that's what we just found here, which reduces down to 3/4. And if you divide 3/4, you get the decimal 0.75 or 75%. And we knew that it was going to be a pretty good chance that you hit a point within this region here because it's the majority of the whole section, and 75% is well over half. Okay? So chances are we did pretty good. Pretty good probability, we did pretty good. All right, now this is going to be using a segment to model a real world probability. We're going to be looking at time. All right, you're going to take a shuttle that runs to town every 10 minutes. The ride from your boarding location takes you 13 minutes. You don't arrive at the boarding station until 2:41, but you want to get to town by 2:57. What is the probability you'll get there by 2:57? All right, well, from 2:41 to 2:57 gives us 16 minutes to arrive. Okay, So step 1, we have 16 minutes to arrive. 13 minutes is travel time. So we have 3 minutes wait time. And those two together equals 16 minutes. Okay, so we only want to wait the maximum of 3 minutes. However, the trains run every 10 minutes. All right, so the second step would be to write a ratio comparing time. I want to wait for 3 minutes, but I could wait for 10 minutes. 3 minutes is equal to 30%. So I have a 30% chance of arriving on time, which isn't very good, because you have which means you have a 70% chance of being late. All right. So to write this down as a probability statement, the probability get to town by 2:57 is the favorable wait time divided by maximum wait time. Not the maximum you want to wait, but the maximum you may have to wait. Okay, lastly, you've got, we're going to use areas to find geometric probability. You know when you go to carnivals and you want to throw something and you have to certain region, and then you get a prize, and the closer you get to that region, the better the prize is. Well, those are all probability types of problems, and so we're going to figure out the probability, what it would take to win this particular game. A golf ball is hit and stops on the green, and this shaded region here is the green. Stops in the painted circle right here. The diameters of the green and circle are shown at the right. If the ball is equally likely to stop on any point on the green, what is the probability that a prize is won? So what they're saying, it could stop anywhere in here. So what's the probability it's going to stop right here? So what we would want to do is find the ratio of the painted circle area to the area of the green circle. Okay? Find the ratio of the painted circle area to the green area. And they're calling this the green, I guess like a golf course, the green. So what we're going to do is we're going to put the probability that a prize is won. The area of this painted circle, the area is pi r squared, and so since the diameter is 15, the radius is going to be 7.5. So 7.5 squared times pi divided by the area of the big circle. Its radius is 37.5 because it's half of its diameter. So 37.5 squared times pi. Now you can simplify that. The pi is going to divide out and square these numbers and reduce them, and you're going to get 1/25. So there is a 1 in 25 or 4% chance of winning. So save your money and don't play the game and go buy a stuffed animal. That's my motto. It's not as fun, but it's more likely you're going to get it. All right. You guys have a great day.